Hiya. So at higher level, you need to be aware of how the number of bits assigned to the mantissa or the exponent can affect the numbers we can store. So this is a quick demo. I'm going to quickly show you. So imagine we've got this number to store on a computer. We're going to store it using floating point representation as a mantissa and exponent. Now, I'm just going to stick to denary here rather than binary, just to make it easier for this example, I think. Imagine we've got 2 digits for the mantissa, and I need to write this out in standard form, scientific notation, floating point, basically all the same thing. Then I'm going to be writing something like that down. Okay? That would be me writing out as best I could. If I'm only allowed a couple of digits for the mantissa, writing out as best I can in that way. That's what I can do as a way of storing it, writing it down in that neat way. But if I expand that out again, then this is what I'd get. Not quite what we had here originally. Now look at if I allow myself 3 digits for the mantissa, then I can do a bit better. Okay, I can write it out like that. If I expand it out, not what we had originally, but it's a little bit closer to it. 4 digits. Yeah, I can write it out a little bit more accurately. Get a few more of the digits in there. When I expand it out, it's not the same, but it is closer to what the original was. Okay, I think you get the point. So as I increase the number of digits that I can use from my mantissa, what I'm doing is I'm allowing myself to store the original number more precisely. Okay, and that's what you need to know. The number of bits that you have available to store the mantissa affects how precisely you can store a number. So it affects precision of the number stored. So if you don't allow enough bits for the mantissa, then you cannot store numbers precisely. Okay? Let's look at the exponent. So I'm going for a similar sort of thing here. We've got this big number that we need to store. If I allow myself 1 digit for the exponent, so I'm going to write this out. The highest possible exponent I can get with 1 digit, just in denary, in our world, is 9. So let's just do that. That is the best I can do. That is the best I can get in terms of representing that, which is just a fraction of the size. If I expand that, it's a fraction of the size of this number that I was trying to represent. If I allow myself 2 digits, then all of a sudden I can actually get the right exponent, and I can store the number correctly. I can store that large number correctly. If I think about if I've got 2 digits, what's the highest exponent I can get? 99. So I can store a number that large with the exponent, compared to with 1 digit I could store a number that large. Okay, so there is a simple little rule. Oh, and I've chopped it off, and I'm not going to do this, start this again. Exponent, the number of bits that you assign to the exponent affects the range of numbers that can be stored, that says. Damn it. So, there are 2 simple rules that you need. The more bits we're assigning to the mantissa, then the more precisely we can store a number. The more bits we're assigning to an exponent, then the greater the range of numbers we can store. As in, we can store larger numbers. So, another thing you need to know and be able to answer questions about is, well, basically what I've said, except if we're told we have, for example, 32 bits to store numbers, then what we need to understand is that if we increase the number of bits that we use for the mantissa, that means we can't use as many of the bits for the exponent. So increasing the number of bits for the mantissa means that you're going to be able to store numbers more precisely, but you're not going to be able to store such a range of numbers. Because if I've got 32 bits, if I say I want to use 24 of them for the mantissa, then I've only got 8 left for the exponent. Whereas if I use 16 for the mantissa, 16 for the exponent, then that means my precision would decrease compared to that first example, but I get a greater range. Okay, so increasing the number of bits for the exponent means we can't have as many for the mantissa, so we get a greater range, but the precision is reduced. And you just have to understand that sort of balance, that balancing act. In fact, I'm just going to look at a couple of quick questions here from, I don't know, old exams. Here they are. So look, here's one. You've got 32 bits for the floating point representation. Mantissa's given 24 and 8 for the exponent. What will be the effect if you change it to 16-bit for each of them? Okay, so that means you're reducing the number of bits for the mantissa, you're increasing the number of bits for the exponent. So that means precision will decrease, but range will increase. Okay? Make a bit of sense? I hope so. See ya.